All right, boys. Hope you're doing well. Looking forward to our next couple months together. And even though we're not physically close to one another, we're still together and working through this together. So here's your next unit, and it is all pertaining to an idea that's called correlation. Correlation is just a general word for a relationship between two sets, usually of numbers. And we're going to look at a series of many different correlated data sets, and we're also going to look at how to mathematically find a mathematical model or regression for these correlations or relationships. So we're first going to start out by describing what a correlation is and what kind of correlation it happens to be. So, we're relating two sets. So in this particular example, we have the diameter of your ankle versus your diameter of your knee, right? And that seems as if it ought to be some sort of relationship between basically how big your ankle is and how big your knee is. So we have different ways to classify correlations. They can be strong or weak correlations or no correlation. We can have a positive or negative correlation, and we can have a linear or non-linear correlation. The strength of the correlation happens to do with how closely the data points are scattered about a line or another function. And so if you look at this particular visual, we have a correlation coefficient. It's called R. And that R is a mathematical value between -1 and 1. And it determines how strongly two data sets are correlated. So in general, the first row of correlated data sets have what I would refer to as at least the first two as a positive correlation. Positive correlation essentially means the trend goes up as the other trend goes up, right? And so we can express that as you can see in this particular slide, a line here that's trending upwards and another line here that's trending upwards. Those happen to be called the line of best fit or the linear regression. We'll get into that later. All right, and you can see that of the first and second graphs, it looks like the first graph has data points that are more tightly centered about that line of best fit. So therefore, we have not only a positive correlation because it's trending upwards, but we have a stronger positive correlation noted by that R correlation coefficient that's close to 1. So the closer that value is R, if it's a positive correlation, is to 1, the tighter the correlation will be, the stronger it will be. If R equals 1, it's a perfect linear correlation, which rarely happens in the real world. Okay. Whereas in number 2, you can see how R, the correlation coefficient, is 0.3. Now that's further away from the number 1, right? We want R, if it's positive, to be close to 1 if it's a strong correlation. So I would say the second data set graph is weaker positive correlation than the first data set, right? You can compare the R values, the correlation coefficients, right? And you can also see visually how more scattered the second data set points are than the first data set, okay? Finally, if we kind of look at the last one and just put a circle around it, it doesn't look like there's any discernible pattern at all with those data points, right? It doesn't look like anything's trending up or down or in any other way that's discernible visually. So I would say that this particular has no correlation, right? And again, that's noted by the R correlation coefficient value of 0, okay? We can do a similar thing. If you look at the second row of data set, there are 3 of them. You can see how they're trending downward, right? And when they trend downward, that means they have a negative correlation, right? And of course, The first one has an R value not of 0.7, but of negative 0.7 because it's trending downward. And if it were a perfect negative linear correlation, that R correlation coefficient would be equal to -1, right? So the closer R is to -1, for a negative correlation that's linear, would be a stronger negative linear correlation than if the R correlation coefficient were -0.3, because -0.7 is closer to -1 than -0.3, right? And just like in the first row, this last scatter plot appears to have no discernible trend, no pattern, no correlation. Therefore, there's no correlation. Okay, as noted by R equals 0, the correlation coefficient. Okay, so the idea is these guys can be positive or negatively correlated, linear, and the R, the correlation coefficient, is a measure that we'll find out later how to evaluate, but it does give us a good test of the strength. The closer R is to 1 or -1, 1 if it's positive, -1 if it's negatively correlated, the better, the stronger the correlation is. Okay, here's an example, supply and demand. Some of you take econ or even AP econ, and the basic idea, the theory for supply and demand, as you can see, is that you have two curves, or in this case lines. So we're assuming by theory they're linear, which may or may not be a good assumption. Sometimes they're curves. But let's just assume they're both linear in theory. And let's take a look at the demand, quote-unquote, curve. So here's my demand curve. All right, and what we have on the x-axis is the quantity, which is the number of widgets that we either the supplier supply or the consumers demand, right? And on the y-axis, we have the price of those goods or services or widgets, right? So the demand curve, noted here, is a positive linear correlation because as price increases, excuse me, wrong. The demand curve rather is a negative linear correlation because as the price of goods increase, the demand for those decrease. And of course, that's noted by the downward trending line. Right? So that's an example of at least a theoretical model for a negative linear correlation. All right? Supply works a little different. So the supply curve, which is our other one in this diagram. Again, same axes. I have the quantity going left, right, price going up, down. As price increases, then the suppliers are more willing or more likely to produce or supply more of those. Right? So the supply, quote unquote, curve is a positive correlation noted by the uphill, the increasing line. So supply is a positive correlation, as noted by the upward line. The price and supply both increase with one another. And similarly, yet conversely, the price demand is a negative correlation because as price increases, the demand for those goods and services decreases, as noted by the downward trending line. We can also have non-linear correlations. Of course, there are different types of functions. We're going to look at this later. This is very relevant today. These are the US cases that I got from that noted website, but that's certainly not a linear trend, right? In fact, it looks like it's exponential, right? Which is why these diseases are so scary, one of the reasons why. Okay, and we're going to look at the numbers behind that. So the number of cases relative to the time looks like it's a strong exponential correlation, right? It doesn't increase at a constant rate like the other linear ones we looked at, okay? The last idea is this notion of an outlier, and sometimes when we collect data, sometimes there might be an error, or sometimes a point or two might not make sense. So this affects kind of the relationship between those two data sets, and this is an example. So kind of the same one we looked at before. You got the size of your ankle versus size of your knee, and the set on the left has 2 points, one certainly, that just don't look like they belong, right? And we can see that it's certainly a positive correlation as noted by this upward trending line of best fit. Okay, it appears to be logical that as one's ankle increases, the size of their knee also increases. So that's a positive correlation. Now, with those potential outliers in there, we might have an R value that's not very strong. So perhaps R for this one is, I don't know, just making up, maybe 0.6. Okay. Now, when I remove those outliers, as I did in the second diagram, the second scatter plot, I get a much better fit. Right? All the points are, now that the other two potential outliers are gone, are pretty darn close to that line. So if I remove those outliers, this might give me a much tighter correlation coefficient of maybe 0.85 or 0.9. Okay? And remember, the closer those correlation coefficient values of R are to 1, the better or more tightly or stronger the correlation, in this case, a positive linear correlation is. Okay, so that about do it for today. It's just some correlation theory. We have this notion of strong or weak, noted by R, correlation coefficient. We want that to be close to 1 or negative 1. We have this notion of positive or negative. In other words, trending up if it's positive, trending down if it's negative. And we can also have linear trends, correlations, but we can also have nonlinear trends like we saw with the coronavirus, a very scary, potentially exponential data set. Okay, so hope you enjoyed this. I look forward to debriefing with you in a class soon. Bye-bye.